talk is something which we did with my colleagues. As you know, as most of our speakers have said, nothing in the industry is done by one person. So I have put all the names of the people there. You cannot see it here, but probably you please look into the screen there. The difference, so most of the first three talks that you've seen has been related with natural language processing. Also something related to understanding the context management stuff. So we do use this kind of concepts in Repsol, but since we are a company with a very specific industrial purpose, what we try to do is that we try to take ideas from these kinds of areas. For example, the sequence-to-sequence methods which Clara and Maria have explained. We try to use it in a dynamic decision-making optimization problem. For example, you want to plan the development of an oil field. So how do you transfer knowledge from one area to that? So that's where most of the creativity of the applied mathematicians in Repsol go. Okay? So in this talk, I will be talking about one such application, a different application. So my focus will be, because this is, so I'm an applied mathematician sitting in a room full of mostly DevOps and developers and maybe people from other expertise. And I'm going to talk about a problem in geophysics, which I'm not expert. So we're going to have lots of fun. So the focus would be trying to give you key conceptual ideas, explain why things work, why certain approaches were done, and present some results. That's the basic learning objective of this talk. It's more like a class. Okay? So, let's get started. And I think I have to proceed hard. Yeah. So, I take the liberty to put two slides about what we do in Tech Lab, and since you might not know, because there was a professor here, Antonio Fernandez, he actually worked with people in Repsol, but he didn't know that there was a group of applied mathematicians in Repsol. So I'll take two slides to explain that. Okay? So, as you can see in this slide, we are around 240 scientists, mostly from the engineering background, in Repsol Technology Lab, where we try to solve the technical problems which the company's business units have. Okay, so that's where the science happens. And I have taken a slide from a particular division of Repsol Technology Lab, which works on open innovation models. And the reason I put that is because probably in the future we will collaborate with some of you. So it's good to know the way things work. Okay? So as you can see, there are two gears there: the innovation gear and the exnovation gear. I think it's a made-up word. Okay, just to contrast innovation. So the exnovation, what I put is basically, okay, if we, for example, fund an external entity. So we work jointly on some problems, and then we try to extract value out of it. And there are several ways to do that. There is a corporate venturing fund of which has an initial quotation of 85 million euros, and every year there is a call for grants. So if you are a startup with great ideas, please apply for these calls, and hopefully you will win some of them. I think. So the other thing is, okay, we do science, we publish, we file for patents and everything, so it's a very good place to be. And believe me, I come from academics. I've been 3.5 years in Repsol, and I vouch for that. You can do science. And we have lots of space, 50,000 meter squares of space to develop the scientific activities that we do. Okay, so what you see is these are greatest asset. That's our people, and you're looking at the advanced mathematics team at Repsol. We are around 22 people with multi-disciplinary background. So the underlying thread is that everybody there is an applied mathematician, but they also have an additional career. Some of them have done dynamic systems, some of them have done computer science, etc., etc. Some of them are in quantum computing. So As you can see, we also have our famous so-called camiseta friki in Spanish. It's a maths t-shirt. So people here in, I think the next few days will have some G on the beach t-shirts. So we are in the same onda, basically, in the same way. So what's the, I'm going to speak about which unifies those 23 people, and that's our vision, mission, and strategy. So our vision is to place, to position Repsol at the forefront of the mathematical technology, so that, and in a sustainable way, so that Repsol can achieve all the grand challenges that they keep announcing. Okay, so this cannot be done without input from, say, mathematics. So that's our vision. And our mission is to deliver high quality products that employ these mathematical techniques and to help our businesses realize value and a competitive edge. So that's our mission. And the strategy is by ensuring that we have a great team. These people, what you see in the screen, are some of the best people I have worked with. And sometimes I'm very happy that when I'm in a room, I'm not the smartest guy all the time. So I do have an option to learn from everyone, and that's most of the time. So, and I'm very happy to say that to you, okay? So, all this I'm saying is that in future, if some of you wants to come to Tech Lab and work with us, this is what you can expect, okay? One more thing, if you really want to indulge into, okay, what kind of applied mathematicians are in Repsol, you can Google my name in LinkedIn, and I have given a course on why, for example, the Kalman filter, which is used often, works. So the details, intrinsic details of this, which mostly you may learn only in very high universities. So we give courses in that. So you'll get insight of what's happening inside the lab. Okay? And with this, that's pretty much it, the introduction about Tech Lab and everything. Great. So, oh no, you have to go back. See, yes, correct. So, as I said before, you cannot see it there because it's a very pixelized image. I think I would suggest that you look at the screens there, right in front of you. The reason I put this is because I think it's fundamental to understand how data is generated and what problem we're trying to solve. Okay? Here, we are looking at a problem where we want to image the subsurface of the Earth. So it's something like doing a big echography of the Earth, okay? But then since Earth is much more complicated than the human body, which is soft and lots of assumptions can be made, Earth is not like that. So what you see, let me see if I can point things. No. The blue part, what you see, is the part which is underneath. Okay? So you're looking at a problem which people call it as it's called a 2D acquisition. It's 2D because one of the dimensions is time, the other dimension is a 1D line in space. So to understand the image, look at the blue part, which is a vertical slice. Okay? So imagine you're here, that's your 1D point, and you want to know exactly how the Earth is underneath. Okay? So, the vertical axis is time, the horizontal axis is space, and you want to somehow take an image of those interfaces which are underneath the Earth. Correct? And why do we need to do that? Traditionally, it has been used for exploration of hydrocarbons, petroleum. Okay? But as we know that Repsol, we are transitioning towards a greener ways of generating energy, and also minimizing our carbon impacts. So I will be speculating right now, but another application of these kind of things is that you know where you can store your captured carbon dioxide. Okay, so you need to know specifically in certain parts of sediments which has a retaining capacity. For that also you would like to know how the subsurface is. Okay. And the reason that is important is that decisions here cost lots of money, of the order of millions. Okay? And imagine this is a section which is approximately 1 or 2 kilometers deep. So you make small errors, you miss a zone, you are, excuse this expression, but you are screwed up. Okay? So you need to have precision tools. So that's why we are looking at this problem, and that's why it's important. What is measured is what you see on the gray part, on the top. The way to visualize that is that, can you play the video again? Allow me to interrupt, because that's important. ¿Podemos volver atrás y pulsar el botón? Correcto. Gracias. So, imagine the gray part which is slowly evolving as you have put a big paper here and the paper is coming out. Okay? So, when you explore, for example, in this problem, there is one seismic source. You can understand it as a dynamite. Somebody has put a dynamite there, boom. Okay? And that generates an elastic wave in the earth. So it goes down, it hits the interfaces, and then it gets reflected. And when the reflected signal reaches the surface, there are lots of geophones which are located on the 1D line that you have put there, which records the signal. So in a sense, each geophone is having a time series of data. Okay? But then nothing is a very strong word, but most of the data that we collect, they are very structured. Again, I'm doing this is lots of money is involved, so we just can't go and gather stuff. When you collect all the data and this analysis. No, we have very planned acquisition design campaigns. So each geophone has a time series of data. So what you're seeing is that these geophones are put together and their output, it looks like that. So that's the data I'm talking about. Okay? So usually if you put all these geophone data as, so we call it traces. So I'm going to define words because when I first started talking to geophysics, I think lots of months went lost in translation. Okay? So I'll try my best so that things are clear. So these are stacked together. I think the matrix is around 2,000 sampling points in time and around 150, 200, 300 points in space. Okay, so that's our data. And like this, we'll have, say, 200 or 300 shots. Each shot is a source. Okay, so if it's a 1D line acquisition, this data is approximately in gigabytes. If it is a 2-dimensional surface, so you have 3D data, the data in each campaign is of the order of terabytes. So I take the liberty to say that in a certain sense it is big data, but it is not big data in the sense of the number of data points you have. Okay? I can twist the tail and say that okay, if you consider each trace, then you do have it. But that's not the case. There's a very, very, very beautiful structure in that. Okay? So now we have understood what we are trying to solve, what the data is there. Now I'm going to give some insight into two problems that we face when we do that. Okay? The first problem is, if it works, so if the figure which is on the my rightmost side, yours leftmost side, that's what you look. That's what you expect to have, the clean data. Okay? But often what happens is that the geophones might not work. Okay? Or there is a lake, or somebody is living close by and he puts an objection. No, you cannot put any sensors close to my house. So this is how we have data gaps. Or the geophone doesn't work, or somebody is objecting, or we just don't have permission. It could be a hill, for example, like Sierra Nevada. Okay, you can't do that. So you have large data gaps, and it's important to remember that these data gaps are trace-wise. Okay, it can also happen that the geophone stops working after some time. So that would be gaps inside the time series gaps, but we will be looking at gaps which are because the traces disappear. Okay, so that's the problem. So there is a second stage of acquiring this data is to process it. Okay, now you're looking at that, and looking at that image, you should be able to say how the interfaces are in the subsurface. So that's a different processing unit, and they have a very funny requirement because the tools that they use, they require you to provide uniformly sampled points in space, because that's how the things they use work. So it can happen that You may be having, say, equally spaced geophones, but sometimes you have to interpolate to provide the resolution which is needed to map the surface. So this is the first problem I'm talking about. That's the interpolation problem or reconstruction problem. The reason I'm saying reconstruction is that people in Seismic, when they say interpolation, they automatically think it is a linear interpolation. And they use reconstruction for something which is higher order. Okay? But in the mathematical sense, it means both of them are the same. So the first problem is interpolation. How can we do the interpolation in a very challenging way? I spent like 5-6 years teaching numerical analysis before we joined university. I was in the University of Manchester teaching numerical analysis and interpolation courses. And believe me, this is the most challenging interpolation problem that I've seen. Okay, so all the theory which was explained simply doesn't apply for these kind of problems. And if you are aware of problems like aliasing, for example, you take a photo and then you want to look into your phone, you see some strange artifacts coming inside, okay? These are called aliasing, okay? So you encounter these kind of problems. So standard interpolation methods don't work, or they give you something which your eye, even you as a human, you mistake. So you need methods that are very efficient. So they are short with big traces, and you want to have that kind of interpolate results. That's the first problem. The second problem is more of an operational concern. Remember, we are putting lots of millions of euros every day to do this. So, a wonderful idea which is offered to the people is that, okay, instead of doing shot by shot by shot, 200 shots, which may span over several days, why can't we put, say, 5 or 6 simultaneous shots? And I'm going to acquire the signals of all of them together. It's a wonderful idea. So let's save some money now. But then the next problem comes, how do I, the processing people cannot work with that. You will have to somehow segregate what would have been the response of these individual shots from a blended shot. So that's the second problem, the problem of deblending, okay? So I'm going to do a small demo so that we understand why this is. So I'm going to come front. I'm trying to improvise, so this is one shot, okay? It's a cartoon, but I think you get the point, right? It's something like that. So I have likewise put 3 shots. So I have a slides with that 3 shots. So sometimes what happens is that you may have to move in a higher dimension or just make a detour to a high dimension to actually solve a problem. So I'm going to transform a 2-dimensional thing into a 3-dimensional problem because that's where we have better insights. So it's something like what, I don't remember who, but he said that the shortest way in the complex plane need not pass through the origin, right? So it's something like this. So to visualize it, because it's important, because if you don't get it, the rest of the thing is nonsense. First shot, let's call this shot number 4. So I have put it in the slot of 4, okay? So this is shot number 7. I put it in the slot number 7, okay? This is shot number, let's say 50, doesn't matter. So like this, if I arrange, you see that? Now I have arranged all these slices in one plane, okay? So this photo, what you see, is what the people in Seismic community say it's a common shot domain, because it's a common shot, and the receivers are receiving. So like this, if I stack them in this way, I generate a so-called seismic data cube. Okay, that is what you see in the slide as P. P is basically this 3-dimensional thing. XIS is a source index. XRJ is a receiver index, and T is a time index. Okay, so this is what we do. Now I'm going to tell you something very beautiful. Okay, so but for that I have to do another demo. So now what we have, okay, the problem is now this is blended acquisition. Remember, the challenge now is to move from here to that stage. How do we do that? So this is a very ill-posed problem. Okay, there are multiple solutions. Great. So I'm going to I'm going to see something, and then you'll be wondering, why the heck did somebody get this idea, right? That you can ask as a question, okay? But I'll just tell you what people do and in the field. What they do is that, so at slide number 4, they multiply this into 3 parts. These are identical. You can see if I put them together, they're the same thing, okay? Okay, they're the same thing, believe me. And then you put them together. So nothing in the physical world is simultaneous, okay? So in this problem, apart from that fact, we on purpose, we introduce randomness. So this is one of the few cases where creating chaos and randomness actually helps. Another application is it's called dithering in images. You know, you want to have low resolution images that gives you good sensation of 3-dimensionality. That's also a place where you purposefully introduce randomness. The way you introduce randomness here is that when you are creating these 3 shots, you introduce a time delay. It's not but something like that. Okay. So you have this, you're introducing that randomness there. That's why in these slides, if you see, I don't know if you can see it, there's a slight misalignment. So what they do is that the geophones, when they measure and they send signals, what they do is that they align it in such a way that, for example, if this is of a particular source, they push it up in a sense that this becomes at time 0. So these things have a different time delay, okay? For this shot, they push it such that the red point is at the time 0. And this final slide is such a way that the blue one is at the time 0, okay? So this process, they call it as pseudo deblending because it's not actually, nothing has been deblended, okay? Now you may think, okay, what shall I do with this? Now here is the beautiful thing, okay? You can't do anything in this common shot domain. But if you take a slice in the common receiver domain, which is basically a perpendicular plane, then you will see that only informations which were correctly placed, they appear as coherent information in that plane. So these things which are slightly misplaced, their contribution actually comes as, say, incoherent information. It need not be Gaussian noise, but it makes no sense. Some data which sits there, which has to be kicked out. Okay? So it's something like an anomaly then. So that's the fundamental insight. Why people do this? Why does it make sense? How did somebody get an idea? I will need more time. I need to put mathematical equations, which I don't want you to go over with right now. But if you're interested, we will talk about it. Okay? So essentially, this can be understood as Fourier transforms, and when you do a Fourier transform, then you transform the physical problem into an algebraic one. And when you're in algebraic one, you will see it as a, an imposed multiple solution answers. So for all the multiple solutions, you do a least square approximation. And it turns out that if you do further approximations for the least squares answer, you end up into this. Okay? But the fundamental result is that, okay, you cut any other plane. Sometimes you can also cut it diagonally. Okay? That's what people call it common midpoint acquisition. Okay? We will not enter into it. Just let's look at the common receiver. Okay? You have information which is now segregated. So this process, I have drawn some cartoons to explain. Okay? So we do a Fourier transforms, and the time signals become frequency signals, and the blending operation can be seen as a linear combination of those frequency data, which can be expressed as a matrix multiplication. And then, so essentially, this is whatever I have demonstrated now is what is shown there. Okay? So let's move. And the problem is this one, simple. That's a cartoon. From a, so you have, instead of short index, you have source group indices. You have to move from there to here. That's the first problem. And this cartoon is basically what I have demonstrated again. Okay? If you want to have a quick glance, essentially it's that. Now, let's see how do we, and this is how a real image looks like. And believe me, so what you see on the right hand side is how the incoherent information looks like in the common receiver domain. And what we want to get is this one. That looks more or less coherent, right? So you have to remove that. So this is what we do, you know. in Spanish, you know, para batir un problema hay que traerlo a tu terreno. No? So you bring the difficult problem, you pose it in your field of expertise, and kill it there. So what we have transformed a deblending problem into a denoising problem. Okay, we have only a few tools to work with. So the creativity as humans is that to pose the problem in that phase. Okay, so now we can apply all the knowledge we have in denoising to remove that noise. Okay, and I'm going to talk about one approach where we use groups, let's say machine learning or deep learning methods. So to the previous speaker, I have asked, so why do you think certain methods work? So this as an applied mathematician, I always ask, because otherwise I just can't sleep. So why do you think self-supervised learning works? Because we are going to use self-supervised learning. Supervised learning requires, first let's see why does supervised learning works. One of the points which we need is that we need somebody to manually clean up the data. Okay? So you have a ground truth prior, and then you train a network to capture these ground truths. And I will bet 100 or 200 euros that underneath what's happening is that the machine learning algorithm is learning a compression algorithm. Okay? Especially if you're using an auto-encoder kind of architecture. So compression, the way it works is that noise is usually high frequency. So when you compress something, you usually remove the high frequency content. And when you decompress, the high frequency content doesn't exist. And that's why you get smoother results. That's the working principle. Okay? That's great for supervised learning. And remember, it's almost impossible for a human to actually clean and provide you information. So that's the justification for going to a unsupervised or self-supervised learning approach. So, heck, why does such a method work? And this is a very beautiful paper. I mean, if you haven't read it, you should read it. Excellently written, few pages. Amazing. The authors, Dr. Watson and Royer, they explain. So, they first define a way of partitioning information. Okay, so they call it J invariance. J like J on the beach. Okay, so the essence of J invariance is that you take a set of indices, you do partition. Partition, for example, numbers 1 to 10. You say you can divide it as 1, 2, 3, 3, 4. Remember, we are doing this source blending. If you are able to design a function that predicts something, and that prediction does not depend upon the value the function takes in that set, that property is called J invariance. And then they say, okay, that's the definition, and then they say, okay, such kind for J invariant spaces, if you set up a self-supervised learning problem, then the optimal parameters of the network which you get is the same as if you had done a supervised learning problem. So that's the last equation which is there. That equation means that. So the optimization, optimal parameters for the self-supervised learning problem, that is f of x minus x, is the same as f of x minus y. That's a beautiful result. So this is the working principle of why unsupervised learning works. Okay? And they showed it with a wonderful example using, say, a median filter. Okay, they removed the central dot, and then if you see the blue lines, the nature in which they change, the optimum is the same. Okay, so that's the key takeaway of this slide. So now we know why these methods should work. Now what is remaining is to set up a J invariant set. Okay, so we are going to use so-called. But the unit, if you directly apply to the denoising problem, it's not going to work, because in the space of solutions which are admissible, there exists a self-mapping. So if you set up an unsupervised learning problem, you may encounter a solution which says the norm is 0 and ciao. Okay, so nothing's false. So how do we modify the unit in such a way that it creates this J invariance? So there is another paper which is down, it's Lane and co-authors. They've actually done this for the standard image denoising applications. So they have modified the unit in a way that you have a central one spot gap. So you'll be using the unit to, for example, predict what is happening at a point, but when you do the convolutional operations, you don't include that point. And there are this many number of ways of doing it. Okay? We cannot do that because if you remember, we have tailored a problem such that the noise is trace-wise. Okay? So if you apply this method straight away, it's not going to work because trace information is coherent and sometimes high frequency, and we don't want to kill it. Okay? So what we do is that we adapt that method in such a way that you have so-called trace blindedness. Instead of just removing information from one point, you construct the convolution operations in such a way that you don't take contributions from the vertical trace when you're trying to predict what's happening. This is another thing. If you are interested, I have so-called blueprints because it's very hard to visualize. So all this is published work. Okay, this is work published in an IEEE journal, Journal of what's called Geosciences and Remote Sensing. So if you want to look at the details, as this gentleman over there requested, all details are there. Okay, even then you find it hard to understand. So if you want to discuss on this, I'm available after lunch. How this is being done. Okay. So this is how we create the geometric sets. So what is remaining now is, now you have to define a loss function. Okay? It turns out that if you use the standard self-supervised loss, it's not going to work. And the reason is simple. The seismic images are funny because when you explode something, that's an explosion. So the displacement that's going to cause will be of the order of 10 to the power of 6, something like that, in terms of decibels. But the information which goes down and comes back up, some of them will be order of maybe a few decimals. So there's a high disparity in the data magnitudes. And when you're doing deblending and when you're introducing these noises, it can happen that the noise has a magnitude several orders bigger than the actual signal. So if you do the denoising without thinking, you may actually kill the true signal. So you can't use a standard self-supervised loss. So you adapt it. The way we do that, again, this is where your engineering background comes, to put some physics into it. Okay? So you can see it here. You're looking in the screens. This term which is here, I think that's this second equation, is where we introduce a physics. So in the loss functions, what they do is that, okay, the network is going to predict something. So assuming that is already deblended data, we apply the physics. We blend it, we apply pseudo deblending, and that is what we are removing from the original solution. So this is the way we implement the self-supervised loss, and we do it in 2 steps. Okay, that will be the first blending loss function, and then there is a thing called we call it identity loss. Okay, so we do it in 2 stages. We train the network to make a prediction, and once that is done, we take the output and the network and then redo the problem. The working principle there is basically, in mathematics, it's called the projection operation. Okay? If you're projecting your information onto a space, and if you project again, you should get the same thing. That's a beautiful property to have, because otherwise, if you keep on repeating the projection, if it not works as a projection, it becomes a kind of smoothing operation. And we don't want smoothing, because smoothing kills everything. Okay? So you would like to know when to stop, and the method stops when it's supposed to stop. So that's basically the key ideas in how we have constructed the loss functions. Now, to deal with the disparity in the data, we scale it, and we have designed, we haven't designed, there's nothing great about that, but the purpose of that is that it should be invertible, it should be a bijective map. So this is one of the scaling functions which is bijective, and it helps us. So we always scale the data before we apply any method on them. So this slide is just to explain that. Okay, so some results. Does it work? Yes, it does work. It works amazingly. I was so surprised. Okay? I'm very skeptical about machine learning methods coming from my mathematics background, but when I saw it, I said, okay, we have tried to get that, and we did it. Okay? So it's amazing how beautiful deep learning things and denoising effects are happening there. Okay? So these are tested on two, they are called synthetic data, but this is actually, these are very good approximations of your real data sets. A consortium of petroleum engineers have come together and they have created simulations of different challenging situations in the Earth, and that experiment was called SEAM. So each company in this area has access to that information, and we train on that. So even though they are synthetic, they are very realistic. Okay? So on that we have tested, and you can see, do you agree that that's beautiful? Yes? Good. What happened? Okay, this is the same visualization, but now in the common short domain. Okay, what if you map back into the real? You can see that you have removed, for example, in this one there is an additional shot here. That shot has been removed completely. Amazing, right? So that's the key ideas behind this. Now, this is something slide just to show that how the two-stage deblending loss function helps. Apparently, it helps a lot. So you have to actually squint your eyes to see the difference between the images. Okay, the one on the right was the prediction second stage is of much higher resolution and accuracy than on the prediction stage 1. Okay, so oops. Okay, now let's go to the problem of reconstruction. Again, the working principle is simple. Denoising and interpolations are at the core the same problem. And so those are the equals and equals. No? So all these ideas, they have same working principle. Remember, why was denoising working? Because we are compressing it and decompressing. When you compress, high frequency gets kicked out. The same idea is used for interpolation. So, and people have been applying traditional, for example, Fourier transform methods. You transform the data in the Fourier domain. We know that, for example, the JPG algorithm is that. It's basically a discrete cosine transformation. And then you just kick out threshold all the high values. Okay? Now we have observed that this is helpful for denoising. So the natural thing is, okay, let's see if it works for interpolation. And it turns out that it works. Okay? The only difference would be, we use the same, the architecture of the network is the same. The only thing that we change is the definition of the self-supervised loss. Okay? The problem that we're trying to optimize. We had to do something additional because when you're doing reconstruction, you have a problem called aliasing. That's because when data is missing, what does it mean when missing? Usually you put zeros there. So you have information that's coming and suddenly there's a drop. And if you're doing a Fourier transform of that, since that's a discontinuity, you actually map it as, yes? You're thinking out loud. No, that's okay, yeah. But that's a good sign, that's a good sign. Thank you. So when you have discontinuities, you have, say, frequencies which are unphysical. And that usually manifests, and you need to take care of that. And one way what we have done is an automatic spectral suppression method. Because we have observed that most of the energy is usually in the, if you do the Fourier transform, it is in the so-called in a conic region which passes through the center of origin of the Fourier transform origin. So we found an automatic edge detection algorithm, and we create a mask which suppresses or which penalizes frequency values outside the band. And that one, if you can see, this image is basically a visualization of that. For the interpolation problem, the loss function is a standard self-supervised loss. That is, you have the data which is x, and then you have a function, that's your network. Function's prediction is f of x. So x minus f of x, that's the loss function. That's a standard thing we use for interpolation. To that, we add a regularization term, which acts like a penalty term. So it penalizes, for example, on the Fourier transform data, you apply a mask, and all Fourier components which are outside the central zone, you add it as such, a norm. Adding a term as a norm, what it does is that the optimization problem tries to minimize it. So what does minimizing means? That that term should be closer to 0. What does that term be closer to 0 means? That your predicted results wouldn't have Fourier components outside that region. Okay, that's how this works. So I think I'm done pretty much. So the message is that the method works and everything is fantastic. And hopefully, I hope that you have learned one application, why that's important, what are the working principles behind constructing machine learning problems, and here are the results. If you have any questions, you want to interact, I'm at your disposal. Thank you.